Welcome back. It's time for Unit 2 as we study Math 109. Unit 2 will talk about logic and we'll do a great deal of work on sets. The content from Louise. The content for Unit 2 comes from Chapter 2 and your textbook. With no further ado, it's time to share. Here we go, PowerPoint. Got it. Da, da, da. Let's try that again. All right, we're going to share the PowerPoint. That's better. All right, let's maximize that baby. That's better. All right, slideshow. From the beginning. Okay, here we go. Unit 2. We'll have a series of, I think, about 5 videos from Unit 2. We'll break it up. Got 3 sections to consider. Here's your overview section. Look, back in the day, we used to do more in logic in geometry in high school setting. With all the changes that have transpired, probably mostly due to standardized testing, I think a lot of places logic kind of got swept out. So for some of you, this might be a new set of content. The set stuff from sections 2 and sections 3 probably will be pretty new for most of you. The good news is it's not particularly difficult. We've got a lot of symbols to get used to. A lot of examples for us as we work through the PowerPoint. So it should be a good place for us. Let's get started, see what's going on. So there's more continuing on the what's in store. The set operation stuff will make use of some Venn diagrams, some good stuff coming along the way. A little bit of work for us, but we shouldn't get scared. As before, we've got objectives listed. I'll let you have a moment to read them if you will, but I'm not going to read them to you. That used to bother me a lot as a student. More from section 2, more from section 3. Here we go. Moving into section 2, and we'll talk about reasoning and logic. A quick intro. We're not going to get too heavy in this. You'll see some truth tables, but not to any great extent. Those of you who may have done truth tables in a geometry setting probably did a pretty detailed amount of them, but we won't get into that. What's up for us? Well, we'll take a look at conjunctions. The connector on those is and. We'll take a look at disjunctions. Again, $1.95 math words. The connector on those is or. We'll look at if-then statements, $1.95 math word for conditional, and we'll try to decide whether an argument is valid based on the premises. All right, words from your teacher. Again, those of you who've done truth tables may remember some angst. We'll not get too crazy. We'll look at very basic ones. You will not be forced to draw any in the course. You will not be forced to memorize any in the course. A little bit of thought should probably get us there. All right, so first of all, let's talk about statements. A statement is a sentence, first of all, that is clearly defined as true or false. There can be no ambiguity. You can't say things like, Del Furster is good looking. All right, not everybody's going to say true. Now, I might say true, and other people might hold up a mirror and say, come on now, that's false. So if it's a statement, everyone surveyed must have this same truth or false statement as it relates to that. They must all classify it the same way. All right, so some more symbols, that little squiggly thing. Generally, you'll see the letter P used to represent the statement, but it's not universal. It can be Q, it can be R, it can be S. If there are multiple statements considered, usually the letters you'll see are P, Q, R, and S. If we negate a statement, that means we basically throw the word not in, and we use the little squiggle there that some of you remember from seeing in similar triangles back in the day. All right, so if a given statement P is true, its negation will be false. And if a given statement P is false, its negation will be true. Quantifiers are words that describe quantity. They are consisting of universal or existential. Universal means all. All men are old. Well, that's probably not true. Some men are old. So the existential some probably fits that statement better than the universal all. So there are some examples on the screen for you. All, some, every. The first and third of those, all and every, are universal, and some and there exists would be existential. All right, a truth table just lists all the possible truth outcomes for a statement or something relative to that statement. So I'm going to show you a truth table for P and the negation of P or not P. All right, so you'll see if P is true, all right, something that might say baseball is a sport with a ball. All right, that's a true statement. So its negation, baseball is not a sport with a ball, would then in fact be false. If the given statement is false, Del Furster is the King of England. Happens to be a false statement. The negation of that statement, Del Furster is not the King of England, would in fact be true. So a very simple truth table for P and not P, considering the true and false natures for those two statements. All right, conjunctions put two statements together with a little symbol that kind of looks like an upside down V. All right, one of my kids once said you can envision putting a little line across that and it makes it an A. And the word that's often read with conjunction is and. So you get one statement and another. And in red, the significance for us relative to conjunctions is a conjunction statement, an and statement, can only be true when both component statements, P and Q, are true. We will look at a few examples to try to lock that down. Here we go. So a truth table first, and you see that P has some truth and false values, and so does Q. And basically what you have there is every possible combination of true and false as it relates to those two statements, P and Q. And then the right side column says what's true about the conjunction P and Q. You'll notice on the first line across where both P and Q were true, the conjunction, the and statement is also true. But if either or maybe both of P and Q are false, then the conjunction statement will be false. So a conjunction can only be true when both component statements are true. All right, so contrast that, if you will, with a disjunction, which uses the connector or. Symbol just kind of looks like a V. And again, two statements are needed, P or Q, that would be read. And in contrast, for conjunction, a disjunction is true if one of the component statements is true, or in fact, if both would be true. Okay, so for a disjunction to be true, only one of the two component statements needs to be true. All right, here's a truth table for you. If P is Q and Q is true, well, then guess what? You've got at least one of them true. So the disjunction or statement would be true. If P is Q and Q is false, again, the disjunction is true because you had one of the component statements being true. So again, disjunction just needs one statement to be true. Conjunction needs both statements to be true. All right, here we got some examples. Number one. 2 plus 6 is equal to 8. That looks pretty true to me. And, so this is a conjunction, 3 minus 1 is 68. Well, I don't think that second part's true. So remember, for an and statement to be true, both of the component statements must be true. In this case, that second one's coming up a little weak. So that and statement will be listed as false. Again, conjunctions are only true when both component statements are true. Our second statement kind of broke down. 2 plus 6 is equal to 3. Oh, baby, this is an or. So this is a disjunction. Or you are a student in Math 109. Holy cow, I think you are a student in Math 109. Otherwise, I'm not quite sure why you're watching this video. The first statement of that, 2 plus 6 is equal to 3, however, is not true. But if it's an or statement, only one of the two component statements must be true to drive the or statement to a true. So the example number 2 would be true. Number 3, your teacher's name is Dr. Furster. I'm here to tell you that son of a gun is true. And so it's back to conjunction. Dr. Furster is a Packers fan. Oh, I don't have any Packers gear right here handy, but trust me, that's a true statement. I can list the Packer quarterbacks going back to Bart Starr. So, all right, it's an and statement. So for the and statement to be true, both component statements must be true. In this sense, I believe that they are, so the and statement is also true. Last one, 2 minus 6 is negative 4. That happens to be true. Or your teacher is a big Eagles fan. There could not be a farther from the true statement. So that second part's bogus. It's not true. It's false big time. But the first part of that statement, 2 minus 6 is equal to negative 4, is true. And since this is an or statement, this is a disjunction, it is true if only one of the two statements is true. In this case, that first statement's true, which makes the or statement true as well. So make sure you're happy on and or. And is a bit more stringent. For an and statement to be true, both component statements must be true. Or is a little more forgiving. For an or statement to be true, one or the other, or both, could be true. That, my friends, ends video 1 for Unit 2. We'll be back soon with video 2. See you then.